Good morning. We'll start our session shortly. As usual, I see some of you already wrote your name on the chat area. Thank you. If you haven't done it, now's a good time. I'll give you, I think the mechanics of the exam went well. I saw that most of you submitted your tests and it went. I haven't started grading them there. First, I'm going to create a rubric that will make things easier for me to grade and then for you to later check up on your exams. Plus, I'm not even done with your previous exam. I'm about to, actually. So I think I will finish with that one today. So your exam, your previous exam is about to be done. When I am, the scores will be uploaded. And for the one we just did, you're gonna have to be a bit more patient. All right, so that's about the exam. Now about where we're going with the course, I'm happy to tell you that we're almost done. We're going to start today chapter 13, which is the last chapter that we're gonna see this semester. A few of you that have to take 250 will continue on learning calculus, multivariable calculus in 2, 3 higher number of dimensions. And this is a little bit an introduction, a preparation for that. So good thing about this chapter is that, well, first of all, in my opinion, is the easiest of all of them. So the chapter 13 on vectors, in my opinion, is the easiest. It is not quite dependent, almost not dependent at all in any of the things we did before. So again, a good opportunity for some of you that were having difficulties with the previous material to start from brand, like a brand new section, right? I mean, it's brand new, and it's an opportunity because we start from the very beginning. At the what we're gonna be doing today is gonna seem probably too easy, but that's okay because it's just the introduction. Okay, so we'll start talking. Let me move on to the screen. We're gonna start talking about vectors, specifically in the plane. All right, so what are vectors? So vectors are objects that have two properties. So the defining properties of a vector, so they have two properties, two defining properties. And here they are. One of them is a magnitude. And this is a real number greater than 0, greater than or equal 0. And direction. Those are the two main properties of a vector. So we say that two vectors are the same, two vectors are equal, and in a moment I'll tell you about ways in which we can actually represent these vectors, all right? Ways in which we can represent them and, you know, make pictures out of them. So two vectors are the same. If they have the same magnitude and direction. As easy as that. And we'll also be going to be talking about quantities, numbers that have no direction. And when we talk about vectors, those numbers, regular numbers, we call them scalars. So scalars are quantities with no direction. So in other words, real numbers. Okay? All right. So this is a little bit abstract, so I'm going to try to make it more precise by looking at ways in which we can represent these vectors. And specifically, so there is one exception. So, well, first, in the way we're going to represent vectors, it is usually with arrows, and they look like this, right? And usually we label the beginning and the end. We call this the tail, and we call this the head of the vector. And this is the vector PQ, and this is how we usually denote it. We put the tail, the head, and we put an arrow indicating where it begins and where it ends, right? And now you can tell, right? And you can tell from this picture that this vector has this direction, is going in this direction, and it has this magnitude, this big, from P to Q. However this length is, that would be its magnitude, right? And the important thing to note here is that two vectors are the same, like what we wrote here, right? If they have the same magnitude and direction. So if I draw this little vector here, and I draw another one here, I need to be careful, where the direction is the same and the length is the same, right? Then these two vectors are the same, right? Even though I draw them differently, they are the same if they have the same length, right? Say for a moment, let's say that this is 1, and so is this, and that same direction, right? Imagine that these two are actually parallel, all right? So there is one little exception, which is the 0 vector. So the 0 vector, so only one exception. One exception, put it with purple. One exception, the 0 vector, right? Because the 0 vector has 0 magnitude and no direction. So think of it as an arrow, but the length of the arrow is 0. And therefore, you cannot tell in which direction it is pointing, right? Because it's not really pointing anywhere. Okay? All right. Now, if this was the end of it, then we wouldn't do much about it with vectors. But the interesting thing here is that vectors are going to have operations. So there's things we're going to be able to do with vectors. And we will be able to add them. And I'll tell you about that in a moment. But the first thing we want to talk about is how to multiply a vector times a scalar. How to, so this is called scalar multiplication. Okay, and this is what it is. It says a scalar. Remember, that's just a number, right? A scalar C and a vector V. I'm gonna write vectors when I want to write, and when I don't want to say the beginning and the end, I'll just, in the book, the way they're represented is with a bold letter, right? But it's difficult when you write things on your own to write bold letters. So instead, what we're gonna do is we're just gonna put an arrow on top, so you know it's a vector. So if we have a scalar and a vector, we can create a new vector, the scalar multiplication of C and V is CV. And what is CV? Which is a vector which has magnitude, absolute value of C times the magnitude of B, and direction equal to B if C is positive, or the opposite of B if C is negative. All right? So in other words, and this is a fancy way of saying the following. If you have a vector, when you multiply it by a number, that's what we're doing, right? We're multiplying a scalar is just a number. If we multiply, say, by 2, what we're doing is we're going to take the vector in the same direction, but make it twice as big. So the arrow will be twice as big. If we multiply it by 1/2, it will be the opposite way. We're going to have a vector in the same direction, but half as big. If you multiply by a negative number, what happens is that you also multiply the magnitude. So if you multiply by -10, what you're going to do is make the vector 10 times as big, but then point it in the opposite direction. All right? You would point it in the opposite direction. So the best way to explain this is to show you some pictures, which I'm going to do in just a moment. But also let me write down the following definition. This is important as well. We say that two vectors are parallel if one is a scalar multiple of the other. And with this, a little remark here is that the zero vector then is parallel to everyone. So remark, the zero vector is parallel to everyone, right? Because you can always multiply any vector times 0, and then it will become the zero vector. All right? Okay, so these are our basic definitions. Now I'm gonna show you some pictures of what is it that we're doing. Let me go back to our book. So here we have an illustration of what I was telling you. So right here at the bottom, we have the vector v, right? And you can you have some illustrations of what happens when we multiply v by some scalars. This long blue one is 3 times v. And why is it 3 times v? Because it points in the direction of v, right? The same direction. And it's 3 times as big. This one, red one, is -2v because it's twice as big as v, but it points in the opposite, exact opposite direction. Therefore, is -2v. And this one over this one over here, this tiny one, the light blue one on top, that one is one half times v, because what we did is we multiplied the length of v times a half, and again, it has the same direction as v. All right? So is that clear how we can make the picture of an arbitrary vector when we multiply by a scale, right? That's what we just illustrated here. And now we can do example 1. So in example 1, I'm going to show you a picture, and we need to write down a bunch of vectors in terms of u and v, right? So let's go to the next page. Okay. And you see the vectors u and v marked right there. And then we want to identify a few others. For example, PQ, right? What is the vector PQ? Right, so if we look at PQ, that one over there, right? So that one, you see, I'm moving it right now, and it's exactly u, right? If we assume that these lines that you see over here are all parallel, and they have the same length between them, then you can tell that this vector PQ is actually equal to u, right? So PQ is equal to u. Write it on the page so we can look it later, but PQ is the same as u, right? Okay, How about now QP? What if instead of PQ, let me put PQ over here for a moment. And then what if I wanted to do QP, right? From Q to P. And you should realize that that's the same magnitude, right? It is exactly the same magnitude. So if I put it right here on top, you'll see that it's exactly the same magnitude, but now it's pointing in the opposite direction, right? So what is QP? QP is -1 times U. So QP is -1 times U. And -1 times U, we like to call it just negative U, right? I mean, it's like an abbreviation of -1 times U. We call it negative U, all right? So that's QP. Now, what about QR, right? What would be QR? Let me move this somewhere over here. Notice that when I move it, it's exactly the same vector, right? It really doesn't matter where it starts. It as vectors, this red one that I put over here is the same as U, and this red one that I put on the top is the same as negative U. It doesn't matter that I move it. So now we're gonna do QR. So from Q to R, so from here to here, right? What is that one? Well, again, I'm gonna move it. And if I move it, you can tell that it points in the direction of V, right? And what is the magnitude that we should multiply this vector V so that we get this new one QR? How big it is with respect to V? Good. Thanks, those of you that replied, Michael, Miguel. Yes, it's twice as big, right? So this QR will simply be 2 times V, 2V. I'll show you the page shortly. And then last one here, we're asked to calculate RS. So let me move this one out of the way. Put it over here, and then let's calculate RS. So we're gonna draw another one, and we start at R, and we go all the way to S. All right. Now, how about this one, RS? Well, see, it points in the opposite direction of U, right? If I put it over here, you can see that it points in the opposite direction of U. And how big is it this time? 3 times as big, right? So yes, that vector RS is exactly -3U. All right? Questions? Okay, let's go back to the page. Here are the answers that we just found, as you were wondering. All right. Okay, so as you can tell, it's not that there is not that much to it, right, to identify vectors in that way. So the next thing we want to talk about is how do we add vectors, right? I mean, there's these two essential operations. One of them was how we multiply a vector times a number, right? Be careful with that. So it's one of the things we're multiplying is a vector, and the other is a scalar, two different objects, right? And now we're gonna see how we can add, and this time is going to be two vectors. So one vector and another vector. What happens? How can we add them together? And I'm gonna show you again a picture that will explain it very clearly with and then we'll talk about it. All right. So here is the explanation of how we add up vectors graphically with a picture, right? And it's as easy as this. So look at the first picture on your left, and over there you see two vectors, the vector u and the vector v. And what we want to know is what is the vector u plus v, right? What happens when we add those two vectors? How can we find the answer to that? And there is two ways we could do it. We could do it with the triangle rule or the parallelogram rule, and they're about the same. And so here's, for the triangle rule, this is what you do. You place one of your vectors, u in this case, and then you take a copy of v, right? I mean, maybe I can do it here. So let's say that I draw on top of v, right? And then I simply move that guy and I put it where the tail of this vector v is now at the head of the vector u, right here. And then you look at where your new head is when you follow this path, right? Where you first go u and then go v. And that long one over there, the red one that you see on the screen, that's going to be the answer u plus v, right? As easy as that. So that's one way you can do it. The other way you can do it is that you put the vector v, you put it right so that they share the same tail. That's what we did over here on the last picture. And then you complete the parallelogram, right? So you put another copy of v here or another copy of v here. That way you create a parallelogram. And then the big diagonal of that parallelogram is going to be the sum. And this one in particular shows you that if I now do the other one, say from, let's draw the vector u. If I draw the vector u, and let me make it a different color. Oops, I don't know how to change it once I draw it. Okay, never mind. So you can tell how in this way, if you do u and you first do v and then u, you get the same as if you first do u and then you do v, right? The answer is the same. In both ways, you get the endpoint of the big diagonal of the parallelogram, right? So that shows you that this operation we just defined this way has this nice property of being commutative, right? If you do u plus v is the same as v plus u. Like we like that in the sum. 2 plus 3, 5, the same as 3 plus 2, right? We like that property. So this is how we add these two. And you can also figure out then the difference of two vectors in the following way. You can either you can consider the negative of a vector. So let me just show you another picture here. Okay, so here's a picture that illustrates how we can do the difference, right? And so if you have the vectors v and u, and you want to do u minus v, right? U minus v, then what you can do is you simply add u with the negative of v, which is pretty much what they did here, right? So one thing you can do is do the negative of v. Let me do it. Let me do negative b. So negative b would be the vector that starts here and ends right here. And I now add this vector with u, right? U and negative v. And if you follow the rule we just did, you get the parallelogram rule, and it would be this one, u minus v. Now, here's a different way of looking at it, right? When you realize that what you can do is take the other diagonal of the parallelogram, right? If you take the big diagonal, you get the sum. And if you take the small diagonal, because this u minus v, the answer, as you can tell on the picture on the right, that u minus v is also parallel. And if you go from this arrow to that arrow, let me draw it, if you go from here to here, right? That answer is the same as the original one, u minus v. So you can put it in here, and that way you can tell the difference from the parallelogram. You can do the parallelogram, the big one will be the sum, and the difference is either u minus v or v minus u, depending on which way you point it. right? If you point it one way, you get the u minus v. You point it the other way, you get v minus u. All right? Let's put this in practice. Let's do a little picture, a little example. Let's do example 2. Right here in this page. This time we have the vectors v and w, and these points p, q, and r. And using operations of addition and subtraction, we want to find out the following other vectors, starting with OP. So what is the vector OP? Okay. So how can we represent OP? So OP, let me draw it. OP is from here to here, right? How can we represent that one as the sum of two other vectors, right? So we need to add some V's and some W's. And you can tell that if you take this one, I'm drawing right now, and you add, go back to the orange, and you add this one, you get what we want, right? So if I add this blue one that I drew with this orange one, I get OP. And what is the blue one? Well, the blue one is 3 times V, right? So the one we want, OP, we can get it by doing 3 times V plus how many times W? 2 times W, right? You're right, Miguel, thank you. So this orange one that we draw second is like the original one, but twice as big. So OP is 3V plus 2W. Okay, I can show it to you on the screen. I just wrote it on the screen, but so 3V plus 2W. Right, now let's go back to the page and do the other ones. Okay, so the next one is OQ. What about OQ? So now we want to go, let's draw it in brown. We want to go from here to here, OQ. Okay, again, using V and W, right? So how do we reach this point over here if we can only move through these streets, these weird streets that are crooked, right? Well, the way we would go is by first going 3 blocks in the, east direction, right? So we would use the blue one, that is V, and we would go from here to here, right? And then go the reverse of the orange, the reverse of W, from here to here, correct? And if we follow that path, we do OQ. So what is OQ equal to? According to what we just did, is 3 times V minus W, right? Or plus -1 times W, that we like to call it minus W. Okay? All right? Questions so far? Okay, last in this example is if we can do QR. So QR seems a bit more complicated. Let's erase everything that we had. So now we want to do QR. So QR is this one from here to here, right? And now again, the idea is how can we represent QR? Well, starting from Q, we go 1 times V, right? We use the blue one once from here to here. And then we use the one parallel to the orange, 2W, but twice as big to get here. So the answer to QR is we go 1V and 2W. Okay? Questions? show the answers. Okay, so these are the ones we just did right now. Every time I change, it gets a little dark. Okay, fantastic. All right, now, as you can tell from what we were doing so far, vectors, you can move them, right? You can move them to, you can put the tail wherever you want. Yes, so you can start them wherever you want, and they're the same vectors. So it makes sense that we consider vectors that are starting at a special point. And what could be a better point to pick than the origin, right? So when a vector starts, has its head, its tail at the origin, we call it a position vector. So here's a definition. Definition, a vector V with its tail at the origin and head at the point v1, v2 is called a position vector. A position vector, or we also say that it is in standard position. That's the other nomenclature that you may have heard. And these numbers, V1 and V2, we call them the X and the Y components. So the first one, it's called the X component, and the second one is called the Y component. So this is the X component, and this is the Y component of the vector. All right, and we obviously say that two position vectors are the same. So U equals, before that, we use this notation as well. We denote it. Here's how we can write a vector in standard form or as a position vector, V1, V2. Now notice that it almost seems like the coordinates of the tail, of the head, I mean. But instead of using parentheses, we're using these little braces like this. Okay, so I see Matt is asking, does the order matter if you end up in the same place? I assume you're asking about adding two vectors. The order does not matter, right? It's like doing 2 + 3 or 3 + 2. When you add two vectors, it really doesn't matter. Now, if you're talking about this, then it matters, right? Because this is the one in the X and this is the one in the Y. So for these coordinates, the order matters. If you flip them, then you don't get the same thing. So the position vectors, U equals U1, U2, and V1, V2 are the same if and only if are equal, I should say, are equal. So once you decide that the tails are the same, that they start at the same point, then the two vectors are the same if and only if they have the same head, are equal if and only if U1 equals V1 and U2 equals V2. So their X component and their Y component have to be the same, otherwise it doesn't work. All right? And now we can also use these to figure out the magnitude of a vector, right? So now we're introducing components, or you can call them coordinates, for the vectors, and then that would be useful in case we wanted to figure out what is the length of a specific vector. Okay, so let's go to the book again to show some other pictures. So I want to go to the next page. page 808 to show you what we just did here with the position vectors. So right at the top of the page, we can tell this nice diagram over here, right? So on the right-hand side, you see a bunch of vectors that are all the same. They're the vector v, right? And you can see them. They're all, well, my screen shows it in the opposite direction, but they all point in the same direction, right? And all of these vectors v. So those are, you can have a lot of them. But if you make it a position vector, then suddenly there's only one, right? When we talk about position vectors, there's only one because you decided now where the tail is going to be, where the starting point of the vector is, of the arrow. And then once you decide where it starts, then it's the only one with that particular magnitude and direction. Okay, so there's only one of them. Okay, and now since we have this over here, let's figure out how we can get the magnitude, right? How can we tell how big a vector is? And that's easy as well. I just need to show you another diagram and you figure out how we can do it. So if you have a vector PQ, like the one you see on the screen, so this vector PQ goes from x1, y1 to x2, y2. What you can do to figure out its magnitude is to simply use the Pythagorean theorem, right? How does the Pythagorean theorem work? Well, you add the two sides of the right triangle, the square of this side plus the square of that side equals the square of the hypotenuse, which is what we want, right? So then the length that we want will be the square root of this length square plus that length square. And what is this length? Well, this point had coordinate x1 and this other point had coordinate x2. So this difference is x2 minus x1, right? So from here to here is x2 minus x1, and from here to here is y2 minus y1. So those are the numbers you add: x2 minus 1, x1 squared plus y2 minus y1 squared, right? Alternatively, if you have a standard vector or a vector or a position vector, then this is at the origin. So you just need to use the v1 coordinate square plus the v2 coordinate square. Okay. So to summarize, I'll show it to you. Here's the statement: magnitude of a vector. So this is what we just learned. If we have a vector with PQ, and when you can get first the position vector that corresponds to that one, that relates to making P the origin. And the way you can do that is by simply subtracting the x coordinate of Q from the x coordinate of P. So you do x2 minus x1 and y2 minus y1. And then the magnitude, which we denote it like this with absolute value. If we do the absolute value of a vector, we mean the magnitude of the vector. And here's the formula that we just deduced using the Pythagorean theorem. Is just the square root of x2 minus x1 squared plus the y2 minus y1 squared. And if you have it as a position vector, then the magnitude is simply the square of the first coordinate plus the square of the second coordinate, big square root of that. All right? Okay, so let's do an example. This will be example 3. And it's right here. It says, calculating components and magnitude. Given the points O, 0, 0, P, negative 3, 4, and Q, 6, 5, find the components and magnitude of the following vectors. So let's write, let me write it on the page. So O is 0, 0, P is negative 3, 4, and Q is 6, 5. Okay, good. So how do we do it? Well, let's start with OP. OP is a position vector, right? So that's very easy. If you want to do OP, because we're starting from the origin, then OP is simply the vector negative 3, 4. That was super easy, right? Not a lot to do. Now, what about its magnitude? Magnitude. Remember that we write it like this, with absolute value, like with the bars. The bars mean magnitude. It's an equal sign. And the way we do it is we take the square root of this component, square, plus that component, square. And so this will be 9 plus 16, that's 25, and the square root of 25 is 5. So that vector has magnitude 5 units, okay? Is that clear? Easy, right? Easy, easy. PQ. Well, to get the components of the vector PQ, remember, what we need to do is make P the origin. And the way we do that is by taking Q. So it's always, let me write it here so you remember. The way you do it is, this is what you should remember, is head minus tail, right? So take the head and subtract the tail in the coordinates. So this will be 6 minus -3 and 5 minus 4. Those will be the components of this vector PQ. So this is 9, 1. Okay? And then all I need to do to figure out its magnitude is take the component, x component, square it, take the y component, square it, add them together. That'll be 81 plus 1, 82. And that's the best I could do. I'm going to leave it like that. Okay? Is that clear? Questions? Okay. Moving along. So how do we, so we learn how to do the addition of two vectors with the picture. And we also learn how to do the multiplication by a scalar with the picture, right? Just make them bigger or smaller, or maybe change to the opposite direction. And we use the triangle or the parallelogram rule to figure out how to add two vectors, right? Like this one and that one. We can, figure out where the answer would be. And now the question we want to do now is, how do we do it algebraically? So instead of using the picture, how do we do it if we have the components? Okay, and it's easy, and that's the next thing we're gonna. So here is how the vector operations look with components. So vector operations with components. And this is going to be very, very easy and straightforward. How does it work? Well, suppose you have this vector, the one with components u1, u2, and v with components v1 and v2. Then look how easy this is. And see a scalar. If you want to do u plus v, the only thing you need to do is you only add the x components and you add the y components. Easy, right? If you want to do u minus v, well, you just subtract the x and y components of v from the x and y components of u. And if you want to multiply a vector times a constant times a scalar, well, again, all you need to do is multiply that scalar times the components. So it's cu1, comma, cu2. Easy, right? And so that makes it so we can solve these problems now without really having to do a picture. But it's convenient to do both ways, or to know both ways, to see how we can represent the same operation or the same in two different ways, with the picture and in an algebraic way. Good. Let's do an example. This will be example 4. Let's leave these rules here a little bit. And this is example 4. Okay, so we have these two vectors. We have the vector u with components -1 and 2, and the vector v with components 2 and 3. And we have a bunch of questions. First, we want to evaluate what is the magnitude of u plus v. Second, we want to simplify 2u minus 3v. And last, we want to find two vectors, half as long as u and parallel to u. All right? Okay. So this time around, we're gonna try to answer these questions with the new way we learn, right? So operating, figuring out the components. Okay, so let's go. Start with the first. How do we get the magnitude of u plus v? Well, first let's get u plus v. So what is u plus v? Well, we said add up the components, the corresponding components, right? So we're gonna add the -1 with the 2, easy. And we're gonna add the 2 with the 3. So this will be 1, 5, right? And then get the magnitude. How do we get the magnitude? Well, the square root of this number square.
And it should be -1.
Should be -1. Let's see. Where?
Because it's a -1 plus. Oh wait, sorry, I was looking at the wrong one.
Yeah.
Okay, never mind.
No problem. So 25 plus 1, square root of 26. That is it, right? Remember, the magnitude is always a positive real number. If you ever get a negative magnitude, you did something wrong, right? The magnitude should be always 0 or positive. Good. So let's do the others. How about, so that was part A. So now let's go towards part B. It says simplify 2u minus 3b. Well, what is u? U is the vector -1, 2. So I'll write it here. And -3b, and b is the vector 2, 3. Okay. Better. Okay, and let's now simplify. So we multiply 2 times that. You remember, that's how scalar multiplication works. You just take the number and multiply by each one of the components. So the first one will be -2, and then 2 times 2, that will be 4. And then here, -3 times 2, that's -6. And -3 times 3, that's -9. And then add these two, right? So it will be -2 minus 6. And then 4 minus 9. So that's -8 minus 4. That's our simplification. Okay. And all right, now how about part C? It says find two vectors half as long as u and parallel to u. Okay, so where is u? U is -1, 2, 2. So first, how do we find a vector half as long as u? And pointing in the same direction, right? Parallel means pointing in the same direction or the opposite direction, right? Meaning, more specifically, parallel means it's a scalar multiple, which suggests what to do, right? We should multiply this vector by some number so that the magnitude of this guy is half as the magnitude of the original one. When we multiply it by, it should be half as long. So what should we multiply by? Well, by 1/2, right? If we multiply by 1/2, we get -1/2, 1. This vector is for sure half the length of that one, right? So that's one of them. Now, how can we find the other one? Well, the other one is if we multiply by -1/2, right? If we multiply by -1/2, now points in the opposite direction, but it's also half the length. So that will be 1/2 -1. And those are the only two positions. There are only two solutions. There are only two solutions of position vectors that have half the length of this one and the same direction. If you don't want position vectors, then it's just you just need to find other vectors that have this position vector, right? Just move it along, right? So you find it somewhere, like imagine that that's the answer, just move it somewhere else. Change the tail so that the vector has the same direction. Okay, great. Let's move it along. So unit vectors. So definition. A vector is a unit vector if its length is 1. Well, that seems like a very, very easy definition. And then now the question is, how can we find a unit vector in the same direction of a given vector? So here's the question. How can we find a vector, a unit vector, in the same direction as V, right? For example, let's say that I give you the vector, say, with components 3, 4. And that's not a unit vector, right? That's obviously bigger than a unit vector because you go 3 units in one direction and 4 units in the other one. So that's obviously not a unit vector. It's bigger than that. How do we find a unit vector with the same direction, right? And what do you think? What is it that we should do? And it's actually easy, right? See, what is the length of this guy? Well, we did it before or something similar. 9 plus 16, that's 25. So this guy has length 5, right? So this vector is 5 units long. So how do we make it unit, but that it points in the same direction? Well, we should. How do we what do we multiply the magnitude so that it goes from 5 to 1? Yes. How do you what number should we multiply by so that it goes from 5 to 1? Yeah, Ashley, you're right. 1/5, right? Let's multiply by 1/5. So if we multiply by 1/5, now we get 3/5, 4/5. And let's just do it to verify it. I mean, I already know it's gonna work, but let's do it. What would be the length of that? The magnitude? Well, it would be 3/5 square plus 4/5 square. And that's going to be 9 over 25 plus 16 over 25. And 9 and 16 is 25, so this will be 1, right? 25 over 25. And the square root of 1 is 1. So this guy has length 1. So in general, the way to do it is super easy. So we did it for 3, 4, but we just sort of learned how to do it in general. The way we do it in general is we simply multiply by 1 over the magnitude of V. So the answer in general, multiply V by the scalar 1 over magnitude of V, right? It's like dividing by its magnitude. If you divide by its magnitude, then the magnitude becomes 1, which is what we want, right? So it's very, very easy to do. So with that, you can now answer a bunch of problems. Like you can find out if you wanted a vector parallel to V of length 17. Well, something you can do is first find the unit vector, and then once you have the unit vector, you can multiply that by 17, and then it becomes a vector of magnitude 17, and it still has the same direction as the original one. All right, so we'll do an example like that. We have, yeah, I think we could do that one. But before I do that, let me just show you on the book a bunch of properties about vectors and vector operations that work in general. So we're not going to go through them right now, but they are important. So let's go to the book. These are the important properties that fortunately are satisfied by vectors and multiplication by scalars. So the first one is these commutative properties. So it doesn't matter the order in which you add vectors, the answer is the same. The second is the associative property. If you're adding a bunch of vectors, you can do the first two and then add the third, or you can do the last two and then add the first, and you get the same thing. So in reality, we don't put the parentheses anymore. You can just do u plus v plus w and do them in whichever order you want. Okay? Now, if you add the zero vector to anything, it stays the same, right? The zero vector, by the way, is the one that has components 0, 0, right? And then it makes sense. If you add 0 to the first coordinate, it stays the same. If you add 0 to the second coordinate, it stays the same. If you add a vector with its negative, one vector with the one that points in the opposite direction, right? So this one with that one, then they're gonna cancel out and you're gonna get the zero vector. If you multiply by a scalar, a sum of two vectors, you can multiply the scalar times the first plus the scalar times the second, the distributive property. And the same happens if you add up two scalars and we multiply by a vector. If you multiply by the scalar 0, you get the zero vector. That's kind of also obvious, right? If you multiply the 0 times the first component, you get 0. And if you multiply 0 times the second component, you also get 0. So you're going to get the vector 0, 0. If you multiply the 0 vector times any scalar, remains the 0 vector. Again, kind of obvious as well. If you multiply a vector times the one scalar, stays the same. And if you multiply by a scalar and then by another scalar, you could instead have multiplied by the product of the two scalars, right? So in other words, if you first duplicate and then you triplicate, is the same as if you sextuplicate, right? Multiply by 6 instead of duplicate and then triplicate. And all of these properties should be more or less evident. All right, so to finish it up today, let's take a look at the previous page and example 5. Example 5, it says find P. So we have these points. P is negative 1, negative 2, and Q is 6, 10. And first question is find PQ and two unit vectors parallel to PQ. So find PQ and two unit vectors parallel to PQ. Let's start with that one. Find PQ and two unit vectors parallel to PQ. All right, so first PQ, that's easy. Remember, is head minus tail, right? Remember that. It's a quick way to know how to do it. So is 6 minus 1 and 10 minus negative 2. So that's 5, 12. All right, and then how do we find two unit vectors parallel to PQ? So Parallel means that it's either in the same direction or the opposite direction, right? So we already know how to find one in the same direction. The only thing we need to do is multiply by 1 over the magnitude. So we need the magnitude. Let's start with that. What is the magnitude? It will be 5 squared plus 12 squared. And that's 25 plus 144. That number, by the way, is 169, which happens to be 13 squared. So believe it or not, the square root of that is simply 13. Okay, so then we should simply multiply by, right? So this vector is 13 units long. How do you make it unit? Well, multiply it by 1 over 13, right? And then it becomes unit. So one solution is 1 over 13 times 5,12. So that's 5 13ths, 12 13ths. That's one. And the other, the one that points in the opposite direction, is when you multiply by negative 1 over 13. And that's negative 5 13ths, negative 12 13ths. So those are two unit vectors. So these are two unit vectors parallel to 5 12. Okay. Okay, so there's parts B and C, but we're already over time. So we'll finish it up tomorrow. We'll do parts B and C and start the next section, right? So again, I want to encourage you to give a little effort. It's the end of the semester, and if you do well in this last exam, number 4, then chances are that you will get a good grade in the class and, you know, have a considerable additional part of the semester under your belt. So I highly recommend to everyone that you put up the effort to work on this last part of the semester, this last chapter. In my opinion, is the easiest of them all. So it's like a gift to have it at the end of the semester. All right. Are there any questions before we leave?
Yeah, Professor.
Yes.
Could you go to the head minus tail thing again, or where did it come from?
Sure, absolutely. So the idea is how you can, let me go. So the question is, how is it that to get the position vector, we do the head minus the tail? Okay, that's Michael's question. And let me go to the book, the appropriate diagram to explain that is on page 808. So look at the blue vector over here, the vector PQ, right? So that's the tail is this x1, y1, and the head is x2, y2. Yes? So if you want to translate that vector so that you want to move so that now the origin is at is the tail. Let me do a little drawing here. So
Yeah.
you want to go from here to here, right? And now what you want to do is move this guy over here. So you know what is the position vector that corresponds to that one. So we're going to put it here. And to do that, now you ask yourself, well, what is now the x coordinate and the y coordinate of the new tail, of the new head, right? And look over here, right? What was the x coordinate? The x coordinate was the difference of these two is x2 minus x1, right? And that's, you go from the head, the x coordinate of the head minus the x coordinate of the tail. That's this x difference. And the y difference would be the y coordinate from the Q from the y coordinate of P. So that's going to be this height over here, right? So the new coordinates of PQ as a position vector will be x2 minus x1, y2 minus y1. And the way to remember it is, like I was telling you, think of the head minus the tail. That's an easy way to do it. Mm-hmm. Does that answer your question, Michael?
Yeah.
Good. Um, anything else, anyone? Okay, good. Good. So I'll see you guys tomorrow, and we'll continue with this. Thank you.